inattentive. So you may have seen much of the work that followed Sims's, costs of information acquisition or endogenous information acquisition. So we're going to be in that, we're going to consider agents who are rationally inattentive. However, unlike Sims, we're going to generalize away from the typical rational inattention cost function. We're going to allow for a much larger class of cost functions that nest mutual information. And this larger class of cost functions are what are called posterior separable cost functions by Kaplan, Dean, and Leahy. And they will show that they nest mutual information as well as many other information costs that people have thought of. Okay, and then in this framework, we're going to allow agents to acquire information about the payoff relevant state. In addition to that, also payoff irrelevant states. So this will look a lot like public signals, and it will be clearer when we get to the model, as well as endogenous aggregate actions. So we're going to think of a rationally inattentive agent who can track not only fundamentals, but also, non-fundamental states, as well as something like, say, an asset price or any other type of aggregation of actions. And then what are we going to do? Well, we're going to, our contribution here is to answer those questions that I posed before, but in order to do that, we introduced two new concepts that pertain to information cost functions. And we call these partial monotonicity and partial invariance. So these are going to be properties of information cost functions that these cost functions can or may or may not satisfy. And they're going to describe how costs of information respond to particular transformations of this information, okay? So, and just at a high level, these transformations are going to be where we move around the conditional distributions of some variables while we keep the marginal distribution of other variables intact. And it's going to say how the cost of information responds when you make these particular transformations. These concepts that we introduce are going to be a generalization of this invariance concept that is found in a few other papers, but also in information geometry. It's also found in this recent paper by Kaplan, Dean, and Leahy. It can be derived from their axiom of invariance under compression. Ben has also worked on this standard concept of invariance, but basically the standard concept is invariance with respect to transformation in all dimensions, whereas our generalization can be a cost function. You can have a cost function that might be invariant in one dimension, but not others, okay? And mutual information, the typical rational inattention cost function, is invariant in this standard sense. Okay, so what are we going to show? So why do we introduce these new concepts of these new properties of cost functions? We're going to show that the properties of equilibria are related very directly related to these properties. So in particular, we're going to show that when cost functions are monotone in payoff irrelevant states, this is going to be sufficient and necessary for equilibria to feature zero non-fundamental volatility. Similarly, we're going to show that invariance and endogenous actions of cost functions is also sufficient and generically necessary for equilibria to be constrained efficient. So we're going to answer, basically we're going to answer those two questions we posed before. When is there non-fundamental volatility? And when is equilibria constrained efficient? We're going to show that it's related to these properties of cost functions. And then finally, that allows us to answer this third question of is non-fundamental volatility synonymous with constrained inefficiency? Our answer to that is no. We show that they're driven by separate properties of these cost functions. But had you used the typical cost function in this literature, mutual information, which is the typical rational inattention cost function, it would impose that they are the same. So you would get an equilibrium with zero non-fundamental volatility as well as constrained efficiency. So by thinking about a larger class of cost functions and defining these properties of cost functions, we're able to say, in what cases you get what, and in what cases you get, other things. And in particular, we're able to show that there are cost functions that can give you one and not the other. Okay, I don't want to spend that much time in the related literature because I don't have much time in this presentation, but I would say the closest work to ours are these linear quadratic beauty contest papers with very specific Gaussian information acquisition. Our contribution here is to have a very generalized rational inattention and be able to define these properties of cost functions, which nests all these other papers, and be able to say in what case you get what. There's also this very recent paper by Angeletos and Sastry, which thinks about Walrasian markets. They have a very similar result to us, which has to do with invariance of the cost function. So basically, if you read their paper, you'll see that there's this very tight connection between when you get efficiency in their paper and when you get efficiency in large games, and how that has to do with invariance of the cost function. Okay, so let me talk about the game. There's a continuum of agents, which we index by I. Each agent takes an action AI, okay, in some set A. This can be multidimensional, can be L dimensions. Payoffs are going to be defined over the agent's own action, the aggregate action, and some payoff relevant state. And what is this aggregate action? It's just going to be the average action in the population, okay? And our first assumption is that A is non-empty, convex, and compact, and then the payoff function U is continuously differentiable on A cross A bar, okay, for all states. Okay, so an example of this would be the typical beauty contest example, which you may have seen. So for example, Morrison Shin 2002, here they have a one-dimensional action and quadratic payoffs, where you have some quadratic loss from being away from the fundamental state and some quadratic loss from being away from the aggregate action. If you take the best response in this game, it's just this linear combination of your best expectation of the state and your expectation of the aggregate action, okay, which is why this game is so nice. It's very tractable. Beta less than 1 ensures that you have a unique equilibrium, and this beauty contest game is nested in many macro environments, such as like price setting, New Keynesian models, as well as some quantity setting models of incomplete information. Okay, so in our game, we're going to have a finite set of payoff relevant states S, which we call the fundamentals. We're also going to have a finite set of payoff irrelevant states R, which we'll later interpret these as noisy public signals, but just think of these as having some payoff irrelevant noise in it, completely orthogonal to S. Agents are going to have some common prior over this exogenous state space, which we call mu0. Okay, so this is going to be a distribution, a joint distribution over S and R, and S and R can be correlated. Okay, so agents are endowed with this common prior over the exogenous state space, but they're also going to have a prior over the aggregate action, and that's going to be endogenous because, so in equilibrium, I haven't defined equilibrium yet, so this is just I'm going to say this and then verify it later. There's going to be an aggregate action function. So this A bar is the aggregate action, which is going to map these exogenous states into the aggregate action. And then with that, we can define the agent's prior over a larger space, which is over both the exogenous states as well as the aggregate action, okay? And this is this prior, okay? Where it's going to be induced by the common prior over the exogenous states, as well as this is the Dirac delta function over A bar, okay? And this is going to be, agents are rational, so this is going to be their prior over S, R, as well as the aggregate action. Okay, now let's talk about information. So agents are going to see signals, which we're going to denote by omega, okay? That's these. And a signal structure, in any paper with incomplete information, a signal structure is simply just a conditional probability of observing a signal. So here we're going to allow agents to have this signal structure where this is the conditional probability of observing omega, given that the aggregate states are S, R, and A bar. And it's in this way that agents can potentially track R or track the aggregate action A bar. Okay. Under exogenous information, so in exogenous information games, an agent's strategy is simply a mapping from these signals to these actions. So you would call this map, we could call this mapping alpha. If I observe omega, I play AI. Okay. In games with endogenous information, that's what we're interested in here, the agent also gets to choose their information structure or their signal structure. So we allow this agent to choose this VI, which is is this conditional distribution, and because it can track R or A bar, this is where basically these agents can pay attention to payoff irrelevant states if they want to. They can pay attention to the aggregate action if they want to. They choose the signal structure subject to some cost of information acquisition, okay? And we're just good, for now, we write this as just the cost of this signal structure, and another input is this prior, mu, okay? And this is a generalization of the standard rational inattention setup. Okay, and we're going to put a little bit of restriction on this cost function in order to be able to say something. So that's where I'm going now. So a signal structure, that's this conditional distribution, and a prior over these states jointly induce an unconditional distribution over signals. Okay, this is an unconditional distribution over omega. And then posterior distributions consistent with Bayes' rule. So what is this? This is, suppose I observe omega, this is my posterior over these states, S, R, and A bar, okay? So we're going to restrict attention to a class of cost functions, which Kaplan, Dean, and Leahy call posterior separable. And this cost function, so this is what a posterior separable cost function looks like. It's essentially an expected value of the divergence from the prior to the posterior. Okay, so this D here is a divergence from the prior to the posterior, and we're going to assume it's convex in its first argument and continuous on it, both arguments. So why are we doing this? So the reason we do this, we put this minimal amount of structure on the cost function, and we're going to make it this posterior separable class in order for us to define certain properties of the divergences. So you can think of cost functions with their associated divergence, and we're going to define properties of these divergences. Now, some of you may be asking, okay, what is a divergence? A divergence is it's like a distance, but it's much weaker than that. Okay, so you can think of it as this weak notion of a distance from one probability distribution to another. So its inputs are two probability distributions on the same space. It's going to be equal to 0 if and only if the two measures are identical, and that's it. That's the only restriction you have on, on what a divergence is. It need not be symmetric nor satisfy the triangle inequality. Okay, and this class, maybe I should have a slide on this, but this class of posterior separable cost functions is very large. So one thing it does include is the divergence associated with mutual information, which is the Kolbeck-Leibler divergence. Okay, so if you want to write mutual information as a posterior separable cost function, this would be the divergence. There's many other cost functions, for example, like the Salas entropy costs or this Fisher information that Ben has worked with. Basically, all information costs that we know of are within this class of posterior separable cost functions. Okay, so just to summarize what we have our framework has basically three departures from a standard rational inattention framework. We have this generalized cost function, so this large class of costs. Agents can pay attention to R if they want. This will be the potential source of non-fundamental volatility and equilibrium. And agents may choose to pay attention to the endogenous aggregate action as well. Okay, so let me just quickly define the equilibrium. So a standard simplification in rational inattention is to equate signals with action. So we do that here. So instead of picking both a strategy for actions as well as a strategy for signal structures, this conditional distribution over signals, you can reduce that so that you're simply choosing a conditional distribution over actions. Okay, so the agent strategy will be this conditional distribution over actions. And in equilibrium, we're going to look at symmetric Bayesian-Nash equilibria. This is going to be a strategy profile of the agents and an aggregate action function, such that strategies are best responses, okay, to their prior. This is saying that these agents are rational. They have the prior that's basically induced by this common prior over exogenous states and the aggregate action function, the equilibrium aggregate action function. So strategies are best responses. And then the mean is also consistent with the average action. So this alpha bar function, which is the aggregate action, is generated from the mean and the distribution of actions of the agent. Okay, so here we're using a law of large numbers and basically assuming that any, like there's the signals of the agents are idiosyncratic. So basically they can decide to correlate on S, R, or A bar, but other than that, they're independent of each other, and hence we can use the law of large numbers. Okay? All right. Equilibrium exists. We can prove that an equilibrium exists. But now let me just talk about where we're headed in terms of giving you properties of these equilibrium. So what is the point of this paper? The point of this paper is to show that properties of the equilibrium are related to properties of these information cost functions. So far, what we've done is we've restricted attention to this posterior separable class, and it allows us to define properties of cost functions as properties of their divergences. The next step is going to define, we're going to define these certain properties of divergences. This is like our new concept, which we call partial monotonicity and partial invariance. Okay, so what are these concepts, or what are these properties? So we want to think about how a divergence from one distribution to another responds to particular transformations of information. So first, I need to explain to you what these transformations are that we have in mind. Okay, so the first thing I want to think about is going from this larger probability space to smaller probability spaces, or basically going to marginal distributions. And for that, we call coursing, and for the opposite of that, we call embedding, okay? So for example, take any joint distribution mu on this space. This is a joint distribution over three things, S, R, and A bar. Let me try, what we want to do is we want to remove information about R and then add information about R back in. So the way you remove information about R is called a coarsening. And all you do is basically sum this distribution up over the different R states. So you basically go to a marginal distribution, gamma R, okay? So this is a marginal distribution defined by mu over S A bar. Okay, suppose you want to add information back. How would you add that back? Well, you need the conditional distributions, okay? So any joint distribution, mu, not only has marginal distributions, but it also has joint distributions. So if I'm adding information back about R, I would multiply by this conditional distribution of R, this distribution of R conditional on S, comma, A bar. And that's this, which comes simply from Bayes' rule, okay? So this would be the conditional distribution defined by mu over R. Okay, so now what we want to do is we don't want to get the original distribution back, we want a new distribution. And what we want to do is have this composition of in which I basically take away information of R, but then add it back using a new conditional distribution. So we do this using a composition of a coarsening and an embedding. So what does this composition do? It's going to first coarsen, it's going to coarsen its first argument in R. So it's going to take away all information about R from that first one. And that gives you this marginal distribution over S comma A bar. And then it's going to embed using the conditional distributions defined by its second argument, mu prime. Okay, so that's this. So I'm basically replacing the conditional distributions of mu of R conditional and SA with that of another distribution, which I'm calling mu prime. Okay, so that's pretty much the transformations we have in mind. Throw away information about R, then add it back in using some other conditional distribution. And by construction, if I did that to itself, if I took away information on R and then added it back using the same distribution, I should get back the same thing. Okay, so just an example of that. Suppose you have two distributions. Let me call it mu1 and mu2. And suppose I'm just looking at the state space over R and S, and suppose they only have two states. Okay, so that's why I can write this in like some 2x2 matrix. Okay, so this is one joint distribution. This is another joint distribution. Suppose I coarsen this one. Okay, so all I've done is to coarsen this, I've just summed over the R states. So I've lost all information about R. But now I want to add back in information using not the conditional distributions of mu1, but instead the conditional distributions of mu2. So if I multiply this by the conditional distributions of mu2, I get this new joint distribution. Okay. All right, so now why have we defined this? We want to now use this compositional operator to think about properties of divergences. Okay, so we're going to say a divergence is monotone in R if, okay, so this is the divergence from the prior to the posterior. Now suppose on the posterior, I throw away its information of R, but then I embed it back using the conditional distribution of the prior. Okay, so I'm essentially replacing the conditionals of R conditional and SA of the posterior with those of the prior. If this operation makes these more like each other in terms of reducing their divergence, then we're going to say the divergence is monotone in R. Okay. There's another concept, which we call invariance, where we say a divergence is invariant in R if you replace the conditionals. So now let's say we replace the conditionals of both the prior and the posterior with the same conditional distribution. Okay, so that's why I'm doing that to both sides of this divergence. Invariance in R says that if you do that, basically it doesn't matter what this replacement conditional distribution is. Okay, so if the prior and posterior share the same, share a common conditional distribution R conditional and SA, then the exact values of that conditional distribution is immaterial for their divergence. Okay, so that's invariance in R. Now we've done this only in R. We've thrown away information about R, put it back in, and use this to define certain properties of divergences. But we can do this in any dimension. We could have done this in S, we could have done this in A bar. So now I'm going to do it in, so for the purposes of our exercise, what matters for us is also invariance in A bar. So I'm going to define this now in terms of A bar in the exact same way. So again, take any joint distribution mu, okay? A coarsening removes information, hold on, let me, like a lot of noise outside. Suppose I coarsen this by removing information about A. That's this, I'm taking out this information about A bar to get this marginal distribution over S and R. And then I can add back information about A. I could do it using the same the same joint distribution, but basically what that is that's a conditional distribution, okay, of A bar conditional on S and R. And then I'm again going to define the same compositional operator, which is a composition of a coarsening and an embedding, which is basically going to coarsen its first argument in A bar, so throw away information about A bar from this, but then embed using the conditional distributions defined by the second argument, mu prime. Okay? And then again, in the same way that we define invariance with respect to R, we can define invariance in A bar. So we say that a divergence is invariant in A bar if this holds, which again is simply just saying that if the posterior and prior share the same common distribution of A bar conditional on S and R, then it doesn't matter for the divergence what that conditional distribution is. So basically these are things that divergences can satisfy or they may not. Okay, so it's just a definition of a property. You know, you may think that it makes sense for a divergence to satisfy this, but you can also write down divergences that don't satisfy these properties. Okay, so how does this generalize the typical invariance concept? Well, basically what we've shown here is that you can define these with respect to different different coarsenings and embeddings in different dimensions. We did it with R, you can do it with A bar, you can do it with respect to S, whereas the standard definition of invariance is monotone and invariant with respect to all possible coarsenings and embeddings, okay? And this has been described in other work, but one thing that you should keep in mind, and which we can show, although I'm not going to show you today, is that the Kullback-Leibler divergence is monotone and invariant with respect to all possible coarsenings. So it's basically, it satisfies the standard definition of invariance. And our generalization is that cost functions can be monotone and or invariant with respect to some, but not all, okay? All right, so that's what we've done so far. We've defined these partial monotonicity and partial invariance properties of divergences. And then the third step is to show that these cost properties are directly related to properties of the equilibria. So there are two things we show in the paper. One is that monotonicity in R is sufficient and necessary for equilibria to have zero non-fundamental volatility. And I'm going to try to show you that today in my last 15 minutes. In the paper, we also show that invariance in A bar is sufficient and generically necessary for constrained efficiency. So unfortunately, I didn't think I'd have time to show you that today, but these are two different properties. You know, these are the ones that I just defined for you, and hence you can think of cost functions that potentially satisfy one or the other, and they're not the same. Okay, so let me show you this monotonicity in our result. So what are we looking for? So we're going to think about equilibria that are driven only by fundamentals versus equilibria that are driven by stuff that are also non-fundamental. So we're going to say that a symmetric Bayesian-Nash equilibrium is S measurable if this holds for all R, which is basically saying that it does not vary in R. And so these are the type of equilibria that we're going to say have zero non-fundamental volatility. If the aggregate action moves with R, then the equilibria features non-fundamental volatility. Okay, so an intermediate result is basically you can construct, so take any signal structure. What is that? That's a conditional distribution of omega conditional on S R A bar. I can take any signal structure and I can remove its conditioning on R while retaining its marginal probability, or while retaining its conditional probabilities of observing omega conditional on S and A bar, okay? And what that is we're going to call that the minimally informative signal structure. So here we're taking out the R dimension. Basically, we're going to remove the signal structure's conditioning on R while preserving the properties of each, the probabilities of each signal realization. Okay, so this is going to be basically the signal structure that pays no attention to R, but everything else is the same. Okay, and therefore conditional on S and A bar, this signal is independent of R. So an intermediate lemma is that if the divergence associated with C is monotone in R, then this minimally informative signal structure, the one that pays no attention to R, is the least costly. Okay? And conversely, if for all priors and signal structures, the minimally informative signal structure is the least costly, meaning that if I, deciding to not pay attention to R, but keeping the signal structure basically the same in all other respects, if that's the least costly thing for me to do, then the divergence is monotone in R. Okay, and this is what allows us to prove both sufficiency and necessity of non-fundamental volatility and equilibrium. So basically, here's sufficiency. If the divergence D is monotone in R, so if the divergence satisfies this monotonicity in R property, then an equilibrium exists that is S measurable, which means that it has zero non-fundamental volatility. So if costs are monotone in R, then an equilibrium with zero non-fundamental volatility exists. Okay, this is sufficiency. And let me give you just a quick sketch of the proof or the intuition for this. So suppose there's an equilibrium that's S measurable. Okay, A bar only depends on the fundamental. It doesn't depend on R. Our best responses, are the agent's best responses measurable in R? Okay, and the answer here is no. Why? So if you think about payoffs, okay, by definition, R doesn't affect payoffs. It's the S that affects payoffs. So there's no reason for the agents to care about R per se, only insofar as it might affect A bar. Now think about the costs. Well, if they're monotone in R, then that implies that any signal structure that I want is going to be basically the least costly version of it will pay no attention to R. So if I just want to pay attention to S and A bar, there would be no reason for me to pay attention to R. That would only increase my information costs due to this monotonicity in R. Okay, so therefore, if alpha bar is S measurable, then best responses are S measurable and an S measurable equilibrium exists. And now let's think about necessity. So an S measurable Bayesian equilibrium exists if and only if the divergence is monotone in R. Okay, so on all priors generated by S measurable alpha bar. So basically, okay, what are we trying to say here? The translation is that if costs are now non-monotone in R, then an equilibrium exists with non-fundamental volatility. Okay, and this goes back to this intermediate lemma I showed you. Basically, if the divergence, this is an if and only if statement. So basically what we're saying here is if the cost function or if the divergence is non-monotone in R, then the signal structure that pays no attention to R is now not the least costly. You would have now a signal structure that exists that would have basically all the same properties except for the fact that it pays attention to R. Okay, so if you want, so let's think about the sketch or the proof or the intuition for this. Consider again an S measurable equilibrium, one that only depends on S. Our best response is now measurable in R, they are, okay? And the reason is not because payoffs, again, payoffs only depends on S, they don't depend on R insofar as they affect A bar. But basically, the costs, if costs are now non-monotonic in R, it's cheaper to pay attention to R conditional in SA. Okay, so agents would like, basically if they want to learn about S or A bar, they also would like to learn about a little bit about R because it lowers their information costs. And for this reason, best responses are now measurable in R, and in equilibrium, this leads to payoff irrelevant volatility in equilibrium. And I think this is kind of a nice example because it shows why R sort of resembles a noisy public signal. It's coming from the fact that agents, they want to learn about S and they want to learn about A bar. That's what affects their payoffs. But in order to do that, it's cheaper to look a little bit at R. And it's almost as if there's, in the extreme case, you would have a completely free public signal out there, which is zero cost to look at. What we're saying is there's this in between here that if basically to learn about S, you want to sort of look at R because it's a cheap way of learning about S, you would do so. And in that case, whatever type of non-fundamental volatility is in that signal, that would show up in equilibrium. Okay. All right, I think basically I don't have enough time to show you this, but I wanted to at least show you the result, which is for constrained efficiency, it's very different. An equilibrium exists that is constrained efficient if, so there are two things you need, two things that are sufficient. Basically, payoffs such that there's efficiency in the use of information. So we have an entire section in our paper devoted to showing what you need to do in payoffs. So basically, the intuition here is you can't, obviously you're going to get inefficiencies. There are many ways to get inefficiencies in equilibrium. Okay, you can have tons of externalities. Like if people are doing things where someone's smoking and that's an externality on another person's payoffs, of course, you're going to have an inefficient equilibrium with endogenous information. So what we want to do is we want to take all of those away, basically externalities that might come from payoffs, which means that we want to make sure that agents, if they're just given information structures exogenously, that they're doing what the planner would want them to do. So we basically prove we provide a sufficient and necessary condition on payoffs such that there's efficiency in the use of information so that we get rid of all those other possible externalities. And then we ask, now suppose you have payoffs that impose efficiency in the use of information, what else more do you need in order to get also efficiency when agents are acquiring their information? And for that, it's what we call this invariance in A bar. Okay, we show one that it's sufficient, but also that it's generically necessary. And the intuition here is basically that if there could be an externality in the sense that I'm paying attention to these variables out there, but I'm not thinking about how what I do affects the aggregate action. And then maybe Ben may also be thinking about, tracking certain variables, but he doesn't think about how that affects the aggregate action because we're all infinitesimal agents. Now that aggregate action matters for all of our cost functions because it affects our priors. Okay, so if there's an aggregate action function that's very, that's very volatile or very sensitive to S and R, that could be different for a cost than a cost function than if the prior is not if the aggregate action function is not very sensitive to S and R. And the only time that these don't matter is when the cost function is invariant in A bar. So basically that happens to be the property of the cost function such that if we all kind of do our own thing, it happens to coincide with what the planner would want us to do in terms of information acquisition. Okay, so that's our paper. So just to conclude, we show that equilibrium with zero non-fundamental volatility exists if and only if there's monotonicity in R. Okay, so payoff irrelevant states. In the paper, which I didn't show you here, there's constrained efficient equilibrium, or an equilibrium exists that is constrained efficient if and only if there's invariance in A bar and also that restriction on payoffs. And then finally, we have like a nice example that shows that you can get certain things, but not the other. So this just drives home the point that basically you don't have to use if you use the typical rational inattention cost function, which is mutual information, you would get an equilibrium with zero non-fundamental volatility and it would be efficient, okay? But that has to do with the fact that you chose that cost function. You could have chosen other cost functions. For example, a paper that Ben is working on with Mike Woodford, basically they're looking at information, Fisher information, and with that you can get non-fundamental volatility and inefficiency. And we can think about other cost functions out there in the literature that might satisfy one or the other. So I think, yeah, so basically to conclude, our paper has this methodological contribution, which is that if you think outside the, outside of the typical cost function used in the rational inattention literature, you're going to find that basically a lot different things can go, and that depends on what the properties are of the cost functions you choose. And there are many cost functions out there that seem more relevant with the experimental, literature than, say, the mutual information cost function. Okay, I think I ended early, but.
All right, well, thank you. That was really a lot, very insightful. So now we're going to move into the Q&As. We have about 15 minutes for that. And one thing I would, well, first of all, I encourage all of you to ask a question. I know you have questions. In particular, those of you, there were some that were coming up in the Q&A function that Ben was answering. Please, it can be really helpful for those to get asked of the whole group. So raise your hand over in the participant, and when I see them, I will unmute you and let you ask the questions. So until we get all those people raising their hands, I'm going to use host privilege and ask a question. So this is really helpful for a framework, and I appreciate this generalization of the cost functions. I think for someone who has spend a lot more time looking at kind of the empirical model, what rational inattention does when we think about real world macro. It would help me if you could talk about some more concrete examples of how this monotonicity or non-monotonicity arises. Sorry about that, in the cost function, and just help me think through how we would see that or test for that in an application of your modeling.
Ben, do you have any idea how to test for these things?
Yeah, so far what we have thought about is two things. So we're interpreting this R thing as a public signal. And so part of the point that we want to make is that there are many macroeconomic environments where public signals, be they economic announcements or data releases or things like that, are very important for how people think about the state of the economy. And so, our view is that those things, like say in the United States, the non-farm payrolls release would be a famous example, could actually be themselves a source of volatility. That is, that the measurement error in the non-farm payrolls should induce aggregate movements that aren't necessarily related to the underlying fundamentals of the economy. And so I think there is, some potentially interesting work to be done, at the, looking at things like subsequent revisions. Like I know that Lucas Karababunis and Gabriel Chodor-Reich have an interesting paper where they think about the discrepancies between the initial and subsequent announcements of, I want to say it's state level unemployment, and relate that to the generosity of benefits. So I think that there is kind of like a role here for saying, what volatility does the noise in these macroeconomic announcements create? On a more kind of micro level, the paper that I have with Mike that Jennifer has listed here is sort of saying, what can we learn in a lab experiment about how people gather information? What properties of cost functions fit lab data? And then what we're sort of doing in this paper is saying, oh, hey, that generates totally different predictions when you put it into a business cycle model. But I think in this paper, we've made that theoretical point that the predictions are different. We haven't said how they're different or quantified that. And that's obviously a big next step that we or someone else should take.
Yeah, no, that's really helpful. So you heard you all, there's more papers here in the application. And I do think, I mean, sad as it is, there's been a lot more measurement error and changes in measurement error through COVID. I mean, payrolls, household surveys. So, you know, there's a lot to, I think, unpack with that. Okay. All right. Seriously, you all, you better raise some hands. Actually, I should scroll. Maybe there are some. Nope. All right. So I'm going to.
Well, I know from the Q&A that Naveen Gandhi has a question that is good.
All
and
right.
he should raise his hand and ask it.
All right. Raise your hand. You've got just a little time to figure out how to do that. And Ralph had a question, or wait, I'm sorry. Morton had, no, sorry. We're going to go to Ralph first. He's going to ask a question, and then really, I do want to see, you know, those Q&A questions come up here.
Yeah, just a quick question on, given that now we have more structure on this cost function, we understand better, you know, how these properties can drive results. Is there some policy implication? So, you know, if I'm a central bank and I'm releasing information, can I structure my information release in a certain way such that I end up in a, you know, efficient equilibrium, because, you know, it's easier for agents to understand, for example, by targeting or by having, you know, more well-explained public information. So can your modeling speak also to this?
I mean, I think, so as long as agents, basically, as long as agents have cost functions that are invariant in A bar and monetary policy. So are you thinking of like firms that are price setting? Okay, I would say this is basically like, if I'm thinking of a model where firms are choosing prices and the monetary policy is efficient in a constrained efficient sense. So suppose information is just exogenous. And then if you want to give agents more information, as long as there's no other, so in that class of models, you are in a constrained efficient equilibrium. Now, if you add information acquisition, as long as cost functions are invariant in A bar, you're still okay. Basically, you're still in a you add in endogenous information acquisition, but as long as cost functions are invariant in A bar, then you're still in a constrained efficient equilibrium. Now now suppose you open, and then in that case, then if you want to give agents more information, it's always welfare improving. Okay, so basically, but this is because I've made payoffs such that there's no payoff externalities. I've made costs such that there's no externalities on the cost side. I'm in a constrained efficient equilibrium. More information is always better. I don't know. Now, suppose you all of a sudden take away cost functions that are invariant in A bar, and you now have externalities on this side. Okay, so now you have externalities coming from the fact that agents basically don't take into account how their actions affect the aggregate action, and that now affects everyone else's cost of information. In that case, there's possible things that you can do with policy to go back to constrained efficiency, but we haven't figured that out yet. So basically, yeah, all we've done is we've shown that if you have non-invariance in A bar, then you have a constrained inefficient equilibrium, which potentially in a model where you think about monetary policy and firms price setting, you can now do better with, with a monetary policy. On top of that, now if I also want to think about, okay, so now suppose you can somehow use monetary policy to implement the constrained efficient equilibria. Now, if you want to release more information, that should be, I would imagine that should be a good thing. That should be welfare improving because you're on an equilibrium where policy has implemented constraint inefficiency. But away from that, suppose you did not use policy now to deal with this new externality, it could be that more information is worse because we're now in a second best world. And that's kind of been found in other papers that have thought about this question. If you're in a second best world, it could be that more information is worse. So
I'd sort of add the intuition, I think, behind the externality we're highlighting is well illustrated in the monetary policy price setting example. The basic issue that's happening when you don't have this invariance in A bar is that firms find it useful when gathering information to look at other firms' price changes. And that's part of how they're learning. And so in a setting where everyone is learning by watching what everyone else is doing, there's this externality that happens where if I take more extreme actions, I sort of signal to everyone else what my information is. And so a government in that setting can do two things. One is to try to induce firms to take more extreme actions. The other thing is to try to crowd out firms' information. That is, if the government provides its own information so that firms don't have to look at each other so much, then this will redirect firms' attentions towards what the government is saying and reduce this externality that way. So just sort of speaking from intuition, I think that there are interesting policy ramifications to think about what people do when the government doesn't provide information, and how, when the government does provide information, they might redirect their attention. But part of the point of our paper is that you can't do this with the standard mutual information cost function. That externality just doesn't exist with that cost function. So you won't get any of that interesting stuff going on. But if you want to tackle that question with a different cost function like this Fisher information one, then interesting stuff can start to happen there.
All right, thank you. That was really helpful. So Naveen, you are up and it looks like you're unmuted, so go ahead and go.
Hi, yeah, this is Navid. So I have a question about the cost function. So the question is, does your analysis suggest that some features of this cost are like more relevant than others?
Or more what?
More relevant than others, like some features of this cost function are more empirically relevant than others.
I mean, I guess I'm not sure what you mean by empirically relevant. My intuition for the monotonicity in R result is that basically R is this public signal that might be very salient. You know, like for example, these either monetary announcements or announcements by the BLS. And for that reason, people pay attention to them because they're cheaper for them to acquire than information about like S itself. But I'm not sure if that answers the question about what's more empirically relevant.
All right, well, we'll leave it there. And Navi, this is one that if you want to follow up in the kind of small group chat afterwards. It looks like we have 3 more minutes. So Morton had a question as well. So why don't you go ahead and close this out in the Q&A?
No, I just thought that like it's maybe a little bit similar to Ralph's question, but so suppose there was somebody out there who could release information, but either in a very like rough or in a very precise manner that may be different in cost. I was just wondering about what would be the intuition about how. So would that presumably depend upon, like, if that was monetary policy maker, how good they thought that information was? Or?
I mean, I guess so. One point of our paper is that there's no, just because there are public signals out there like R, and those create non-fundamental volatility and equilibrium, it's not necessarily that that's inefficient.
Right.
So basically you can have so suppose you have a business cycle model where firms are choosing quantities and firms are choosing price and potentially nominal prices, and they get information from a public signal and they pay attention to that public signal because they have cost functions that are non-monotone in R. As long as their cost functions are also invariant in a bar, which is a completely separate property, that equilibrium can be efficient. It would be the same as what a planner would do. And if that's true, if they're using and acquiring information efficiently, then more information is always better.
I'm just thinking, like, if you release more precise information that's costlier to obtain, then you get fewer to listen to it, no?
Yeah, I think I share your intuition, Morten, that, you know, there's sort of one question, which is, should the Fed or ECB provide information in addition to just changing interest rates? And how should it provide that information? Should it provide very detailed information that might be hard to process, or very high level information that might be easier to process? And then, you know, there's this interaction. If we think about the ECB or the Fed's information as this R, this noisy public signal, does that crowd out the agent's attention on other people's actions, the A bar, and actually increase efficiency? Or maybe not. Maybe it's what the cost was invariant, so it didn't matter. Maybe it wasn't invariant, so it does. I think what we've done in this paper is to try to kind of guide you towards what information costs are going to generate interesting answers to your question, and what information costs are just going to collapse it all away so that it doesn't matter. And so, you know, yeah, I guess that's what I have to say about that.
Hey, all right. Well, thank you again for a really interesting seminar and for everybody who was asking questions and participating. So I put in the chat the link to a Zoom for a small chat afterwards if you wanted to ask anything specific or just say hi to our two co-authors. And otherwise, thank you again, and we'll see you all again next week. All right. Thank you.
Where? Hold on.
Oh, yeah, I'll leave this open for a little bit. In the chat at the very bottom, there's a link to another Zoom meeting. So you'll have to leave this one